All right, we have the pleasure of Ralph Showalter from Oregon State University talking to us, and he's an expert in porous flow problems, and it's going to be interesting to see what you have for us.
Good. Thank you. It's a pleasure to be speaking to this community on something which they are already expert on. I'm going to tell you about the motivation for a theorem which has been proved, okay, and published. But I put the statement of the theorem. I'm not going to mention the proof. I put the statement of the thank you. I put the statement of the theorem at the very last thing. So if I don't get to something, that'll be it. But mostly, I want to tell you about the motivation for the problem. Okay, and as we go through the motivation, I'll tell you what sorts of things I'm allowed to assume and have the theorem still hold. And the theorem says, yes, this is a good problem. There exists a unique solution which depends reasonably well on the initial data. And in fact, it's a dynamic problem, and the dynamics takes place in a space which is dictated by the problem itself. Okay. So, there's an outline that'll be repeated from time to time. I want to spend most of my time on part one. Part two will be a kind of a extra, and part three, if we're lucky, we will not get to it. Okay, the classical BO system. The BO system was sort of set up to describe filtration flow through a deformable porous medium. So the filtration flow means Darcy law flow, Darcy flow. The porous medium. Deformation meant classically elastic deformation, but our intent is to go well beyond that. Let me start by reviewing the classical linear problem. Okay. So here we have the pressure of the fluid in the channels, okay? That's the Darcy part of the problem right there. So the Darcy flow, if it's a rigid medium, the classical problem is a diffusion equation with the fluid source to drive the flux of fluid, whose divergence is given by the time derivative of what's accumulated in a small cell. And I'm assuming that the fluid is slightly compressible, and the C1 up there contains the porosity and the compressibility of the fluid, which is slight, and possibly any compressibility of the grains of the medium if they are compressible. So all of the sins have been wrapped up in one little number there. The second equation describes the deformations of the material. Second derivative of the displacement, okay, or rate of change of the momentum. So this is our momentum conservation equation. This is the shorthand notation for the elasticity, which is given by a tensor acting on the strain. And then we take the divergence of that corresponding stress. Again, the stress is given. I'm doing an isotropic homogeneous material to keep life simple. So the stress-strain relationship, Hooke's law, is written right here. And this term right here represents a divergence of the stress given by that function of the strain. It's the classic linear model, the Navier system, for describing a linear elasticity system. So if I had this equation by itself with no fluid in it to worry about, this would be my momentum equation. And that would be basically a vector-valued wave equation. And these two are coupled together, and the coupling is right here. What this means is the rate at which the the divergence of the strain rate, the dilatation or dilation rate, becomes a source of fluid. That's the part when you have a saturated sponge on the table and you hit it with your fist, the water goes flying out everywhere. That's the source of water. You're squeezing the water out of the material by dilating the material. On the other hand, the fluid pressure gradient is another addition to the stress, so that's a contribution to the momentum equation over here, and that's the way it's coupled. This is the classical BO system, one of the two forms studied. This is the form that one would use if you include inertia, which would be the case only if you're doing seismic type problems. In other words, where you have a stress-driven situation. You're hitting it with a pulse and you're tracing the wave going through something. Okay? The problems we're interested in here, or at least the ones I was initially interested in here, and I think the ones we're interested in here, it's the only thing I've heard, well, not the only, but anyway. We would like to ignore that term to drop it out. And by the way, the theorem at the end, which we might not see, allows us to set that coefficient equal to 0. It just changes the space in which the dynamics occurs, but the same theorem is still true. So I'm allowed to set rho 1 equal to 0 without losing any of my results, just that the results look different. Okay. The main interest here is in the structure. Now, we have a parabolic problem and either a wave-type problem, hyperbolic problem, or if that's gone, an elliptic problem. So we have a coupled system of equations of different types. That means there's a structure, and I'm looking for a common structure. And that'll be a theme throughout the whole 30 minutes. In other words, find a common structure in which equations of different types all fit together. Okay. Yes?
What's the difference between U1 and U?
The difference between U1 and U is a typing error. Thank you. And that occurs at least one more time. And I didn't see this one, but I saw the other one. Okay.
Now it's a couple of places you have only U at the bottom also. But it's all deformation.
Right. Exactly. That's the one I saw before. But anyway, if you take that as a definition of sigma dependent on a quantifier, so it has nothing to do with the problem. That one's okay. I can live with that. But the one above is a mistake. Right. Okay. Okay. U equals U1. When it's important to distinguish, okay. All right. U equals U1.
Yeah, but U dot U1. U dot.
Okay. So we have a parabolic problem, and if that's gone, it's an elliptic problem, elliptic operator there. If that is there, it's a wave type, and they're coupled across here. Notice the form of the coupling. That'll play an important role throughout. You saw that starting last Wednesday morning, where we have an operator and its adjoint appearing in the off-diagonal terms in a 2x2 matrix. That's the structure sitting right here. The operator gradient and the divergence is a negative of the adjoint of that operator. That structure is going to appear all over the place today, and it's been we'll exploit it here. And in numerical analysts have been exploiting that now for 30 years or more. Okay, so this system, well, all right. So anyway, so this is a classical linear BO model, and I want to look at it in a different way. In particular, I want to look at the boundary conditions that go with it. I've copied the system over here, but this time I wrote the minus the divergence of the permeability times the gradient of the pressure. I've written that as this elliptic operator here to shorten the notation. Maybe I shortened it too soon. I could have saved that till you'd seen it a couple more times. There's my elasticity operator and my diffusion operator there. So my parabolic equation, wave or elliptic equation there, and the coupling terms. What are the boundary conditions that should go with that? On the boundary, I partition the boundary into two parts. This part's classical. Part of this is classical and part's not. I partition the boundary into two pieces, one on which I'm going to prescribe the pressure, and a second part on which I'm going to prescribe flux. This is a normal flux term that you get out of this elliptic operator here, and I'm going to get another contribution, which I'll come back to in a minute. Actually, I'll tell you right now, I get a term that looks like this. That's the normal, let's see, the normal displacement rate on the boundary. And I'll come back and describe that in detail in a minute. I have a second partition of the boundary into two pieces, gamma 0 and gamma traction. So on gamma 0, I specify that displacements equal to 0. These are the conditions that come up from this guy here, together with this one. I have a displacement equal to 0 on part of the boundary. And on the complementary part of the boundary, I have this stress balancing condition. So you can see the stress there, and that's a normal component of the normal stress. Okay? And yes, okay. So, what is this number beta and these two terms here and here? That was part of the reason I got into studying this problem. Let me point out what's going on here. If my medium and its flow paths are over on the left side, and this is the boundary, I've sliced through that porous medium. On the boundary, I should keep track of what happens to all those little flow channels. Sometimes, most of the time, I'm going to cut many of those channels. Other places, those channels may be actually almost parallel. So when I slice through there, I'm going to basically expose some fraction of those channels. Beta is a measure of that. So the number beta, and it can change from point to point on the boundary, is the surface fraction of pores on that common boundary which are sealed. On those, the fluid contributes to the stress. That becomes part of the stress that I have to establish. That's why this term is here with a coefficient of beta. It's only the sealed channels that become contributions to the stress. The rest of it is fluid flowing out, and I'm assuming that the thing is not jacketed. In other words, that the fluid could flow out if it's exposed. And how much flows out? Well, there's the amount that flows out. And in addition, I have another contribution to the fluid flow because of the solid that's moving. My velocity here is relative to the solid. So everything is relative to that. Okay, so in that context, this term here is measuring how much fluid is being moved across that boundary, okay, by this linearized displacement, okay, which is carrying that fluid. And that depends, of course, on how much is exposed to the outside, because that's the part that's going to be seen if I were on the other side measuring the fluid coming across. Okay, so this beta is a parameter which measures basically how many of the channels have been exposed to the outside, and its complement is those that are contributing to the stress. You have to break up into two parts. By the way, this came about sort of backwards from the modeling. When I was trying to figure out what are the right boundary conditions going through a usual tedious integration by parts exercise, terms like this sort of came up naturally, and I asked myself, what do they mean? And after a while, when I was sort of looking at the calculus very carefully, it became clear that this is the way to interpret that. Okay, so this was sort of reverse engineering. And I was interested in that issue because the question that I was really after to answer was, how do you couple a deforming porous medium to an adjacent free fluid? So I had to know all of those quantities quite well to make a reasonable coupling. And I should say that in almost all the classical literature, when you partition the boundary, you partition it with these two, and then you partition it with these two. Those are two independent partitions of the boundary. In all the classical literature, either that set where the fluid was allowed, where the fluid could drain, or where the stress balance held, that set there was always empty. Or, yes, right, that set was always empty. If you look at every classical treatment of the BO problem, that set would be empty. So you would never see terms like that. They would never come up in the equation. Right. But it's clear that they've got to be there. Okay. So looking back on it, what's some of the history of the theory of these problems? My favorite treatment of the fully dynamic problem here, the one that's appropriate with vibrations, the stress-driven problem, was done by Constantine de Fermos in 1968 in a beautiful paper, which unfortunately was addressed to thermoelasticity, which formally has the same set of equations, but instead of pressure, it's temperature. And you can go through some energy, some formal energy calculations and come up with that same set of equations to describe thermoelasticity. But unfortunately, that's sort of the mathematician's formula for thermoelasticity. Everybody who practices thermoelasticity knows that this term is, which one is which? Okay. Right. In this one, this term is usually deleted because you don't generate a significant amount of heat by those dilation rate, by that dilation rate. That's comparable to rubbing sticks together to make a campfire. Okay? They're just not generating enough heat to contribute here. So this term is, this equation here is usually uncoupled by, that's set equal to 0, it uncouples the heat equation, so you solve that independently. Then you use that for data to feed it in here. And this term is significant because the temperature gradients do affect the stress. They are contributions to the total stress. So in the thermoelasticity problems, most of the time that term is equal to 0. And in the Bowley-Wiener text on thermoelasticity, they give a scaling argument to show that if you could justify deleting that inertia term here, the same argument justifies deleting that term right there. So for the quasi-static problem, which is the one of interest mostly to us, in the thermoelasticity context, you would never have that. They would never be coupled. On the other hand, for poroelasticity, those terms are comparable and they're both very strong. They're essential parts of the problem. And in fact, back in the days when Terzaghi, the founder of soil science, one of the pioneers in soil science, was in a debate with one of his colleagues named Fillinger over whether that constant in there, they agreed that there was a constant that was common to both. The question was, is it equal to 1 or is it a small number? Terzaghi said it's equal to 1. His competitor said it's a small number. They got into a public debate. His competitor lost debate and committed suicide. Took it seriously. So be careful with those constants. That constant is there, and it's almost 1. Okay? I like to think it's 1. By the way, what does that mean? The term up here means if you squeeze a sponge, it pops out as much water, just about as much as you've changed the volume. Okay, you can't avoid that. And it's a very strong term. And this is certainly, we agree that that's a strong one anyway. Okay. For the quasi-static case, where the inertia is deleted from that system was derived by Jean-Louis Ariot and Enrique Sanchez Palencia in '72 in a beautiful paper in which they got that by homogenization from Stokes and Navier systems, okay, for the problem. Anyway, it was a result of homogenization. They obtained that equation, and as a corollary from the system from which they derived it, had an existence proof built in. So that was a very nice start for that business. And I didn't get into it till much, much later when I was addressing the question of how do we couple that to something else. And I was interested in boundary conditions, so I looked at it more carefully. And I did some of the janitorial work to sweep up behind. Okay. Let's worry about the constitutive relationships. Elasticity is not enough for every problem. Even soil science demands something better than that, maybe especially soil science. Hooke's law, I wrote originally as the stress is equal to the usual elasticity tensor times the strain. I want to invert that to write it this way, where M is now my compliance tensor. Okay, so I'm going to write Hooke's law in this form by using the inverse of the usual relationship. Okay, so that's the elastic compliance. Tells me how soft the, that's the resistance term there. Okay, tells me how stiff it is. The M does. The reason for writing it that way, if I differentiate that with respect to time, you've probably guessed by now that a dot over a variable means a time derivative. if I differentiate that with respect to time, I haven't given up or gained, I haven't changed the information. But if I differentiate with respect to time, so that's the first and last pair there, I can add to it another operator. By the way, the L is allowed to be 0. That's not going to change any of the theory. But what adding, and I can also add in an L. But what that L represents is a friction term, and you'll recognize that as a viscoelastic model of Maxwell type, I think it is. The classic model which displays creep and other sorts of good things that we like to have in some of our models. If you use a bounded linear operator, you can consist of, this can be a simple ordinary differential equation which says that the stress is an exponential follower of the strain. Okay? You could use a system of differential equations. You could write your stress out into many different components, each of them decaying at different rates, add them all back together and shove them in there. So you could basically have a simple, very simple system of ordinary differential equations there, all just an uncoupled system, but they all have a common input. Then you take the outputs of all those and just add them all back together. And by the way, this operation of giving them a common input versus pulling out the sum of those in the linear algebra context, that's an operator and it's dual. That's that same structure we're seeing over and over again. I could also allow the L to be nonlinear, and I could get very, very brave, in fact, and allow the L to be a maximal monotone operator, which means it's linear, it's multi-valued, it could be degenerate. It's basically, it has to be a monotone graph. That's the only thing. That allows us to include models of plasticity. And since I can do systems here, I can do sums of viscous terms and plasticity terms. And this, I claim that if you allow that to be a maximal monotone operator, in fact, even if you restrict it to be what's called a subgradient operator, that means a very generalized derivative of a convex function, which is not necessarily differentiable, but just lower semi-continuous. Equations like this can be used to describe almost every plasticity model that the engineering community has been interested in. To round out that remark, I would say look in the book called Computational Inelasticity by Simo and Hughes, which is in one of the Springer series. And basically that whole book is about how to write plasticity models in this form and then discretize them and then solve them, et cetera, et cetera. Okay, so I will take it, if I can include models of that type, I can get lots of interesting viscous and plasticity models. And also in a context which is suitable for computation. Okay, let's look at what we have for our system. I'm going to rewrite it in the following way. There's my original diffusion equation. There's a coupling to the deformation. Here's my deformation. I've added an extra term. Let me forget about that for the moment. And over here is what used to be my elasticity term. If the stress was given as terms E times the strain, that would be my original elasticity operator. But now I've just written it as a divergence of the stress. And now the stress is given by solving this system here for the strain. So my single elasticity operator, which was here, has now been replaced by this expression here together with that line. And if I ignore this term here and set L equal to 0 and integrate this equation here with respect to time to write stress directly in terms of strain, that would be the original model. This one includes that as a special case when you set L equal to 0. Okay? But I'm allowing now to have the L in there, which gives us the viscous and plastic behavior in addition to the other. This is a very general strain additive model for the mechanical deformation. And by the way, I could put another similar operator. This F here plays the same role as that elasticity operator did, but I could allow that F to be nonlinear. And when I have these two terms here, that gives me stress additive contributions to the deformation. So I can do both strain additive and stress additive contributions, and I claim you can probably get every such viscous plasticity model that you really care about built into this formulation. Okay. The system in this form was done independently of what comes later. 2004, and a paper with Ulysses Stefanelli. So that's some work that's showing its age, but it's still very relevant. Yes?
What's capital Y?
Pardon?
Capital Y?
Yeah. Lots of sins in there. The Y was the parameter space. I said my stress could be, yes, that's a parameter space for my different components of stress. I'm getting really fancier. Instead of having a discrete family, I'm doing a measurable family, so you can really get some exotic examples. By basically taking lots of lines and taking the upper envelope, you can get convex functions of your choice. And that's one way to generate some. Okay, so that's basically, it's just a parameter space. And the model, in fact, the model is still interesting if Y is just a single point. In other words, you can just ignore it. It gets the flavor. The point is, in a common structure, how much can you build into it? And this is really doing quite well. Any other questions at this point for the, I'm writing the same thing down again, but a similar system that we all know very well, similar in structure. The slightly compressible Stokes system. It's kind of covered up here, but suppose the compressibility of the fluid is 0. That term is gone, that term is gone, and so it says the divergence of the velocity is equal to, could be 0. Divergence of the velocity is equal to any distributed fluid sources. That's a conservation of fluid mass, if C2 is 0. If C2 is not 0, that's just saying it's a slightly compressible fluid. C2 is the compressibility of the fluid. So as a special case, I'm allowed to choose C2 equals 0. Doesn't change anything at the end. If C2 is 0, that's just the incompressibility condition for the Stokes equation, which is right here. There's a momentum term, the pressure gradient, and right here is my friction term, okay, which is written out in this more general way. If it was an incompressible fluid, this guy would be gone, and that would just be the shear viscosity times the Laplacian of the velocity. More generally, you have another contribution, which depends on the slight compressibility of the fluid. So this is a slightly compressible Stokes model. And again, as a special case, just set C2 equal to 0, and you've got the classical Stokes problem. But I can do them both here together, because later on I'm allowed to choose C2 equals 0. Nothing changes with regard to the statement of the theorem. Okay, and again, I call this F to suggest that that's a friction term. So this is the way I'm going to write the Stokes system. It's generalized in a useless way.
You had omega 1 and then all subscripts 1. Now you have all subscripts 2,
yes,
right?
now it's 2.
You'll have them both.
Oh, you're ahead of me. Yes, you're ahead of me. Here's omega 1, a porous medium. Okay, and here's omega 2, sitting over here somewhere. Okay. So now the 1s and 2s are significant. And I'm saving V's for velocities, and if I had U's, those would be displacements. But one of the things I'm trying to do is suppress the U. And I claim that the right thing to do is to set the problem up in the stress and velocity variables. The displacement variables are going to be only velocities. I'm not doing anything in terms of the strain itself, just the strain rates. Okay, so now we have two systems of PDEs. Here's the BO system. I've gone one step further here. I took my diffusion operator and wrote it in a mixed form. That's a choice, whether I do it that way or the way I had before. I can leave that as an A operating on P1, the diffusion operator acting on P1, or I can split that divergence of gradient up into a pair of operators. This Q here is the inverse of permeability. So this is Darcy's law right here. The Darcy flux is equal to minus K times the gradient of pressure. And Q is just K inverse. So that's where I've disguised the Darcy law. But you've been seeing that ever since Wednesday morning. Okay, second line is the momentum balance. where the stress is given by this general relationship here, which I'm tired of discussing by now, and you're tired of hearing about, but there it is. So that's the deformation, and of course they're still coupled, labeled with the Biot constant C0, which couples those two terms, and likewise there's another operator in the negative of its dual form right there, and so on. And right. And there's the minus divergence, and there's minus the gradient acting on the guy. So there's another pair. So I have three sets of operators and their duals floating around this form already.
Constant C naught is the same, right? The complex constant is the same. It's important mathematically, I believe. In symmetry of the system.
Well,
the coupling terms in both equations contain the same constant C naught.
this C0 and this C0 are the same. Those are the two. Those are the original couplings that we saw in the original two single equations. See, originally, this equation was just doing elasticity, and that was folded into that term, and only that one was left at the end. And originally, this guy was folded into there for a single operator on P, and that was the only term left. So this term and this term were the last two that you saw at the very beginning. That's where they were started. But now I have a choice. On these other operators, I have a choice. I can split them up into other pairs if I wish. And again, that's an option that we have. Depends on whether you want to use a minimization method or okay. The pairs are not. You have an operator and its dual matched against each other. They don't contribute to anything, give me estimates, but at least they add up to 0 so they don't hurt. Okay? If I had left it as a full operator in there with a pair of them, then I'd have coercivity estimates, which is stronger in some sense, but not so general in others. And I hope I come back to that theme in a minute. Second equation, on the other domain, here's my generalized Stokes equation. Has the very same form as the one before. You can go through here and almost identify corresponding terms. And that's the beauty of writing this. I took a sort of artificially more general Stokes equation, and I wrote it down right next to this really well-extended Biot system. And you see they have, the way I've written them now, they have essentially the same structure. That was the whole point of getting here. And the second point is, I've split these composite operators up into the way that God gave them to us. We were given conservation laws and constitutive laws. We chose to substitute one into the other to get a second order equation. That was our choice. Maybe it wasn't the greatest choice. If we give a certain linear algebra problem to a freshman, okay, they got a problem with two unknowns, two equations, two unknowns. The first thing they do is eliminate one of the variables and have a more complicated problem. It's now second order. Okay, so they've traded in linear algebra problems for polynomial problems. Was that better or not? Well, in the old days, all we could do was solve Laplace's equations or variance on it. So every conceivable model anybody ever wrote down always ended up with the Laplace equation or the wave equation or the single transport equation. Okay, we're well beyond that now. Okay, so by writing in those basic components, we can now see what are the right things, right physics of the problem. The physics is displayed right in front of us. So if we take these two systems, it's not hard from this point to figure out how to couple them together. By the way, let me point out something else before I move on. I told you this guy could be grossly nonlinear. That was the possibly the viscoplastic term in the in a deformation. The corresponding term down here, that could also be nonlinear. But this is a guy that goes into the Stokes stress. That means I can do a non-Newtonian fluid as well with the same structure. In fact, I could go to something wilder like even the Bingham flow, where it's a combination. Some places it flows, some places it's locked up into solids, and stress intensities tell me which one is which, with hidden free boundaries in them and so on. So this can, by letting C2 be a maximum monotone operator, which is allowed in the theory, this can include really wild things like that, which we can certainly imagine uses for. Here are the interface conditions. if I look at that set of equations I just wrote down, each of those equations gives me a corresponding interface condition. Here's a matching of the, what have I got there? So this is a stress balance. This is a that's a fluid balance between the two. And these are normal stress balances here. Notice these coefficients. By the way, I made a mistake here. That guy should not be there, but instead there should be a beta over there. But this is going by you so fast you wouldn't have noticed that anyway. I'm just admitting there's another typo.
I was going to say that.
Okay, thank you. Yeah, you were just going to say that. I saw your hand up. Nobody else is looking back, but I'll say I saw your hand up. Okay, so that's a normal stress balance. And there's a tangential stress balance, and this condition here is a Beavers-Joseph or Beavers-Joseph-Saffman condition. We can do either here. So basically, these are the now classical couplings for a Darcy-Stokes flow, but now they've been supplemented with the corresponding equations for the deformation, and it all fits together. Okay. Not too long to suffer. Let me back up. Yes. I want to go all the way back. The poromechanics problem. Okay, so this is a 3-minute intermission. So the question where I want to address is, what does the mantle know about mathematics? Where do I start this? Suppose a highly nonlinear stress-strain relationship. I can set m equal to 0. Okay? And that says the stress is some nonlinear function of the strain rate. By setting m equal to 0, I took that deforming medium, which was viscous and elastic, and I threw away the elastic term. Now it's only viscous. If I set m equal to 0, I'm effectively looking at a nonlinear fluid, a non-Newtonian fluid. Okay? So setting m equal to 0 means that the medium is a fluid, not necessarily Newtonian. I have some natural couplings in here. I can set rho equal to 0, which means I'm ignoring the inertia in that generalized fluid. Very viscous fluid. Very viscous fluid. In fact, I have two more than I need here. I have a nonlinear f, and I also have this contribution up here by eliminating the sigma. So I have two different sources of nonlinearity. I really only need one. There's a repetition there. Okay? This one looks nicer because I can do lots of systems more directly. The question is whether I want to write out that viscous term as a second-order term or a pair of first-order terms. I have a choice. So there's a highly viscous fluid coupled to diffusion going on within that fluid. Diffusion of another fluid within that fluid. So I'm asking myself, what's missing from what I've been hearing? Well, lots of things are missing, but if I wanted to adapt this to go ways, what I'm really missing is how the porosity gets into this. The porosity's sort of hidden in there in at least that term. There are other places too where it appears up, but basically the porosity is missing. Well, where is the porosity in this model? Well, it's not there directly. It's there indirectly through this term. If I take the time history of the dilations of that big viscous fluid, if I take the time history of that, I've got a measure of the porosity. Now, by taking a time history, I'm sorry I'm using this word, but I'm getting a compact representation of the porosity, and a compact in the sense of appropriate operators in the mathematical sense. Okay? In other words, it depends on not on the point-wise values, which can be sensitive, but on the history, which changes relatively slowly. So that means that that porosity sitting there is a very nice, smooth function, or functional, history functional, of that term. Okay, so I'm going to stop there, and I'll go back and think about it, and if you get any ideas, I'd like to know what you think about that. But this looks to me like a candidate at least to discuss a model of the type we've been talking about for a while. Okay, onward. I promised you I would minimize the time left for the theory. I'll just show you the pictures, the cartoons. General model I've set up. I had a set of displacement variables, my Darcy velocity, my velocities in the two different of the deformation. This was the velocity of the deformation in which that Darcy flow was riding, and I have the velocity of the free fluid in my model over here, and I put a forced condition. This is a stable condition, or the forced condition, which is allowed by a choice of spaces. In other words, that's a interface condition that I put between those two regions. I force that one. And so that'll be built into the definition of my space. And then I'll have another set of variables, pressures and stresses. Those are my stress variables. Some happen to be pressures, they're special ones. But anyway, I wrote down all those stress variables. So my displacement variables, my stress variables, and if I do that, every one of the systems I've written down so far takes this form right here. Okay? I'll have a principal operator, I'll have a resistance or friction type operator, a friction type operator, some evolution terms, something acting on a time derivatives of the various variables, either the velocity variables for momentum or the stress variables for the conservation of the fluids or whatever, okay? And then I had all these off-diagonal terms which always occurred in the form of an operator and its adjoint with the appropriate sign. And these across here were my friction variables. And and the theory says those guys, these diagonal terms can be very nonlinear. The theory works. They have to be monotone in the appropriate sense, but they can be very nonlinear. They can be multi-valued as long as they're monotone. Monotone graphs. So they're my nonlinear, possibly nonlinear operators, but monotone. And there's an operator, and the negative of its dual appears in that off term. And the requirement on the B is that it have closed range. That's equivalent to the nth soup condition that you've seen before, at least a half a dozen times this week, usually in a numerical setting where it really is a stability estimate explicitly, and here it's an estimate which gives you information to prove your existence theorems. The D1 and D2, so this guy has to be linear, otherwise the B prime wouldn't make sense. That pair has to be linear. Div and grad are the only ones we see. They're linear, of course. These guys here have to be non-negative. That means they can be zero, or zero in part of the place, and bigger than zero somewhere else. They have to be non-negative, linear, symmetric. That's a restriction. As long as those are symmetric and non-negative, everything's going to work. But those two guys there are the ones that determine the space for the dynamics. Of course they are. They're the ones acting on the time derivatives. Okay, so roughly what does it say? Oh, the system I wrote before, if you write out what those, if I write it in my pair of operators, this guy's nonlinear, that one's a linear symmetric, that guy's nonlinear or friction type, that one's linear symmetric, non-negative. And this guy's my operator, linear with closed range, same ones I had before. I can write him out as a, with the pairs A and C, given that C is a diagonal matrix. Those are both friction type operators, and so the C is a friction type operator. And the script A that I had here includes all those other pieces of information here. Notice that this guy here is also symmetric. This guy is symmetric because I have the same sign there. But those are all allowed to be nonlinear. So I could even have a nonlinear condition imposed on that interface condition, which comes up dual to the one I imposed. I imposed one condition, and then the equation gives me my complementary condition when I integrate by parts. That guy can be nonlinear, and I can add to that one in various ways. I did not take advantage of that. I just left the terms I had before. And the corresponding B operator, which has to be linear, doesn't have to be symmetric, good thing, because these are off-diagonal terms without partners over here. It's not symmetric, but it'll have closed range. It's all made up of divergence and gradient operators. Okay? Looking at components and comparing them, and most of the time just comparing it with a classical Stokes problem, I can get a closed range condition on that guy. But again, it depends on the specific problem and so on. Nothing is free, but it can be cheap. And the theorem says, yes, if everything is in place like we said before, we have some conditions here. Number one says that the pair A plus B has to somehow be coercive over one of the spaces. And the second one says, B has closed range and satisfies the M sup. And the third condition says that the pair D2 and C, with the C is here, comes in this term, C plus the, this Y prime, I didn't dwell on that, but it comes from the D2 here, that pair has to have some kind of coercivity condition. And these are generally the second and well, the first one's usually pretty obvious. This one depends, okay. Most of the time it works in all the examples I care about. So then the bottom line is the stationary problem, there's no time to it. The stationary problem has exactly one solution. And then the big theorem says the corresponding evolution problem, there's d by dt of those terms, plus those guys there. That corresponding initial value problem has exactly one solution, and the dynamics takes place in a pair x1 prime, x2 prime, which is determined by that pair of operators, so it's just enough to make sense out of the evolution equation. If you really care about the details.
What we call stationary problem, you just erase
I erase, right. So, right, think Laplace transforms. If you Laplace transform, you have lambda where there's a d by dt, so you're doing a stationary problem. This is the corresponding time-dependent problem. Okay? Or if you take this problem and do a backward difference in time, and take the previous time step and put it on the other side of the equation, that stationary problem is the one that you want to solve to get this guy. Okay. By the way, I can scale the d1 and d2 by any positive number, and it doesn't change any of my hypotheses. So this, what I had before for the stationary problem is exactly the equation that you need to solve for each time step. That's not the efficient way to do it, but in principle, that's what you can do.
Non-standard meaning of station, right?
Right. Right. I just listed the stationary one because if you can't do that one, you can't do this one. Okay. On the other hand, if you can do that one for every positive number in front of that d by dt term, then you can do the time-dependent problem, because that just sets you up to use the backward difference formulation. But anyway, thank you.
Do we have a couple of questions?
So you mentioned the work, right, in analysis, nonlinear PD analysis.
Yes, yes, exactly. Yes.
Valencia. So essentially, from a mathematical point of view, I understood these models, if the models are rightly defined, then the machinery goes through, right?
Right.
This mathematical routine, right, goes through essentially.
If it satisfies my hypotheses, and all of the ones I've been talking about before satisfied those conditions.
So the proof of this theorem would follow, right, more or less the sort of
it's independent of everything I've said before. No, it's a totally different track, but yes, it's true. All right. And it's in that paper in the Sign Journal of Math Analysis.
Monotonicity assumptions are crucial, right?
Yeah, the key thing is monotonicity, right. And it's been done, and I did it without any compactness arguments, so in principle those could be supplemented, and I'm kind of hoping that from the remarks I made, from the guesses I made, dreaming I did before, and maybe that could be used here to supplement this one. Monotonicity and compactness frequently go together quite well.
So you said that this formulation could encompass a wide range of viscoelastic plastic models. Are there any, or could you use this to distinguish between badly formulated viscoelastic plastic models?
If they're badly formulated, they probably would not get into that form.
Okay.
Now, if I can get them into that form, then they're good. In fact, as a special case of the whole theorem, that equation I wrote for the M and the L, for solving for sigma in terms of the strain rate. That's an evolution equation with the very same type of this theorem here. So the theory is an easy application of this one right there. So if you can get it in that form, it's a good problem. I only have good news. It's after 5 o'clock. Who would want to have bad news?
Any lost?
Returning to this non-stationary problem and then remark you made on stationary in your meaning when you erase derivatives. But I thought that, I mean, as you all know, stationary normally means solution of non-stationary problem independent on time. Therefore, you
Yes.
throw out the whole terms, right?
Yes.
Won't your theorem still your theorem requires d1 and d2 to be non-negative? Right?
Yes. They could be zero.
Zero is good
It
enough.
could be
right?
zero.
D1,
But
D2
if they're
is
zero,
good.
some of my hypotheses depended on the D1 or the D2 being added to the other operators.
Right.
So they can only help you, they can't hurt you.
Right.
Now, in the case where D1 and D2 are both equal to 0, then these two spaces, x1 prime and x2 prime, become 0. And on the right side, I'm only allowed to put zeros for data. And then it's a trivial evolution problem. It becomes a stationary problem again. So the space in which the differential equation lives is that dual space sitting on the bottom.
So the conclusion is that your result does apply to the stationary problem in conventional.
Yes, but only with the homogeneous right side. But yes, right. Now, so the stronger or the bigger are the D1 and D2, the bigger are those dual spaces, which it has to be because the range of those operators gets bigger, and it's the range of those operators is exactly where you want to solve the problem. Okay.
All right. I think that brings quite an interesting day to a close, and let's thank Ralph again for an interesting talk.
Thank you.